Good afternoon, everyone. On behalf of Sartorius, I would like to welcome you all to the EU GMP Annex 1, What is Important in Fill and Finish webinar powered by Sartorius. My name is Nurul, a conference producer at IMAPEC, and I will be your host for today. I would like to share a little bit about us. IMAPEC strives to be your one-stop shop for the biopharma industry's business intelligence and networking opportunities. Over the past 16 years, we have established ourselves firmly as a trusted organizer of high-quality biopharma B2B conferences and exhibitions in Asia Pacific and beyond. In the recent 5 years, we have exponentially expanded our portfolio to include digital marketing solutions, market research reports, and our webinar series. Today, we are hosting the EU GMP Annex 1, What is Important in Fill and Finish. In this session, our expert speakers will guide you through each step of the fill and finish process, from freeze and thaw, final formulation, and final filtration to final filling, while breaking down the specific Annex 1 requirements associated with each stage. You will gain practical insights into what regulators are looking for during audits and where the most observed common gaps and risks lie. We will also share how Sartorius supports these requirements, including recommended approaches, technologies, and best practices to help you strengthen your contamination control strategy, improve operational efficiency, and stay inspection ready. So, here is a quick introduction on Sartorius. Sartorius is a leading international partner of the biopharmaceutical industry and the research sector. Known for its innovative solutions, Sartorius specializes in providing cutting-edge laboratory and bioprocessing equipment, as well as services that enhance the development and manufacturing of pharmaceuticals. With a strong commitment to quality and sustainability, Sartorius supports its clients in making scientific advancements that improve human health. I would like to express my heartfelt gratitude to Sartorius and our distinguished speakers for making this webinar possible. Thank you so much for your time and commitment to be part of this webinar, and to all of our attendees, thank you for taking the time out to be with us here today. Before we start, here are a few housekeeping announcements. We strongly encourage everyone to submit their questions by using the Q&A function at the bottom of your screen. And please ensure your name is visible so we can follow up with you directly. Our speakers will be answering them during the Q&A session right after the presentation. So now, without further ado, I would like to introduce our speakers for today. The first one, we have Nivedita Shetty. Nivedita is a product specialist for freeze and thaw technologies at Sartorius, India. Supporting customers across the APAC region, she brings over 10 years of experience in the biopharmaceutical industry with strong technical expertise in single-use systems and downstream processing. Since rejoining Sartorius in 2019, she has specialized in freeze and thaw applications, working closely with pharmaceutical and biopharma customers on process design, scale-up, and best practice implementation. Next, we have Laura Peng. Laura is product specialist, fluid management technology, mixing and storage system at Sartorius, Taiwan. Laura has over 9 years of experience in biopharmaceutical manufacturing. She worked as a key account specialist at Merck and then joined Sartorius as an F&T product specialist with expertise in design, operation, troubleshooting, and technical support in the biopharma industry. Laura is also skilled in optimizing biopharmaceutical processes through the strategic integration of single-use technologies. Next one, we will also have Michael Sartorius. Michael is currently the product specialist for normal flow filtration at Sartorius for the APAC region. He has been with Sartorius for 13 years and brings over 20 years of experience in the pharmaceutical and biopharmaceutical sectors. Michael's expertise encompasses filtration, single-use technologies, quality assurance, validation, and sterile manufacturing. He is a recognized subject matter expert in pre-use post-sterilization integrated testing of filters and frequently presents on this topic at regional conferences. Michael also recently concluded his term as the president of the Parenteral Drug Association Australia chapter and contributes to the PDA. And last one but not least, we have Dixon Chi. Dixon is a product specialist or product excellence FMT Asia at Sartorius, Singapore. Dixon joined Sartorius as APAC engineer to order project leader, designing custom single-use solutions and ensuring GMP compliance. In 2025, he became the Asia fill finish product specialist, supporting stakeholders and leading the business strategy for the fill and finish portfolio in Asia. Dixon is also a Lean Six Sigma Green Belt and PMP certified. So now, let's welcome our first speaker, Nivedita. Nivedita, are you here? All right. Nivedita, the floor is now yours.
Good afternoon, everyone. My name is Nivedita, and I'm the product specialist for freeze and thaw products for the APAC region. What are we going to be talking about today? As the name of the webinar suggests, it's going to be what the regulators are looking for in a fill finish arena, and especially pertaining to the Annex 1. Now, Annex 1 has been in circulation for a while, and people in general know the basics, like having a contamination control strategy and having a QRM in place. So we did not want to go through the introduction into the Annex 1 again, and instead we want to highlight on some of the key principles of the Annex 1, and also what are some of the common observations from the regulators during audit. So, uh, so let's get started. And before we deep dive into these topics, I figure it will still be beneficial if we can have some recap of the Annex 1 and some of its key principles. So, what is Annex 1? Annex 1 is basically a specific subsection of the EU GMP, which is dedicated to the manufacture of sterile medicinal products. And it was created in 2007, and it had about 16 pages back then. In 2022, it underwent one of the most significant sterile manufacturing update in the recent years, and it now has about how many 52 pages, and it also has a glossary. A lot of topics have been added, and some of them has been revised as well. Some of the most notable ones, I would say, would be the contamination control strategy, room classification, qualification requirements, then particle and microbial limits, PUPSIT requirements, barrier systems, and some of them like that. Um, Moving on. So, how does this affect our industry? Historically, many of the facilities approach like sterile manufacturing, like from a procedural compliance point of view, or in that mindset. If they had an SOP and a batch record was complete, the system was considered to be compliant. Okay. However, there has been a new shift right now. Regulators now expect that the facilities shift from reactive investigations to more like a preventive control. And to do this, the facilities need to prove that they understand contamination risks scientifically, and they have to implement a holistic system that employs a science-based approach towards risk analysis and risk mitigation. One of the key observations from the regulators that we hear is that facilities that cannot clearly explain their technical rationale, often they fail during, the inspection. Even if they have a documentation, they fail because they do not have the rationale behind it. They do not understand the rationale. Okay. So now we know that the regulators are looking for proactive sterility assurance rather than a reactive approach, right? So now we can understand the regulatory mindset much better. So usually the inspectors, the regulatory inspectors, of course, they will ask questions like, can the process consistently maintain sterility? Is the contamination prevention designed into place, like they have thought of all the points that they have to think to if there is any aspect that is going to involve a lot of manipulations, example. So have they thought of these kind of aspects when they're designing the process? Are the operators introducing any unnecessary risk? Or like, is the company really using the risk management process when they think, do they keep that in mind? Okay. So regulators are usually evaluating whether this entire manufacturing process behaves like a contamination control system. They're also evaluating your process understanding, and not just like the documentation, but how much well you understand. Then, if I've noticed, human behavior and intervention control, these are some of their major themes when they do any assessment. This is what they're looking at. So, and regulators also recognize that humans are one of the biggest contamination sources in the aseptic processing. Okay, so now that we know what the inspectors are looking for in the QRM and the CCS approach, the risk mitigation, we can look into what is one of the first and the most common contamination risk, and that is the human factor, right? So the Annex 1 strongly emphasizes intervention reduction, that is like less of manual intervention basically. So they strongly emphasize intervention reduction because the regulators, they recognize that every manual activity, it is an opportunity for some kind of contamination to happen. Okay, so that's what is one of the major points that they're looking to. Then we move forward into fill finish. So this is what the topic is all about. So let's focus now into that. So one of the easiest ways to reduce human interventions in the fill finish arena is by the introduction of single-use systems. Okay, so come, let's look into the single-use systems that's being used in the fill finish aspect. Uh, Okay, so the major advantages of having a single-use system is that they are closed. They do not have, they are already predefined. They do not have that much of manipulation required. The system, they are already in made especially for their specific purpose. And of course, there is no CIP or SIP in place because of course these come gamma sterilized or x-ray sterilized, so they don't need anything. They come pre-assembled, so less of human intervention, no misassembly, no concentration of products on the sides, and all of this of course makes it much faster to the market. Also, what the suppliers are, when a process gets more and more into single-use systems, it becomes the supplier's duty to handle most of the sterility related validations, making sure that the operators are trained, and that there is a reliable supply chain. So there's a long-term supply issues are not taken into, they are not they're not a bother for the end user as such, but it is up to the supplier. And then, as you can see, there is the training that is involved. So, operator training majorly falls under the supplier. Now, if you see in the Annex 1, knowledge and experience has been mentioned at least 19 times, and that means that it's quite important that the operators are trained well. Right. Uh, so in this slide, you can see how across the entire fill finish process, we have the single-use products that can be put in place. The first step that you see is the freezing step. The fill finish formulation step in most cases involves a drug substance that has been frozen, which then has to get thawed and then goes into further formulation, and then puts it of final filtration before it is being into the final fill finish, right? So I will be, of course, I have my other colleagues discussing the latter aspects of this process. So I will mainly stick to the first step, that is the fill finish, freeze and thaw of the fill finish, and let's move on. Huh. So initially, if what was in the industry was mainly reusable products that is being used for freezing. What we mostly see is bottles. So freezing with bottles, you can see in here in the slide very clearly what the concerns when freezing with bottles is. So when you freeze with the bottle, for example, you see that the concentration is not even. You see the lowest concentration near the walls, and the highest concentration is at the center and at the bottom, basically cryoconcentration. Okay, and this can cause a pH shift, and this may affect the product stability. Okay. One of the easiest ways you can avoid this kind of cryoconcentration happening is making sure that your product is frozen or thawed in a fast manner. Okay, and fast manner. So you can use equipments like plate freezers or blast freezers, which will ensure that and the process of freezing or thawing can happen at the earliest. So, a plate freezer, for example, makes use of conduction technology with the heat transfer fluid passing on the plates from on top and bottom, and ensuring that the single-use container placed in between them has a maximum amount of conduction happening, which causes the heat transfer to happen at the fastest rate. You also have freezers like the blast freezer, which works on it provides like convection as a way of having the heat transfer happen. Both of these ensure that there is consistent freezing and thawing controlled, as well as consistent freezing and thawing possibilities. Okay, moving on. So, see, there is an increasing. I mentioned that the observations from the regulators, right, in the very beginning of the webinar. So, we also see that there is what the different things that the regulators look into. So, one of the things that they look into, and we are seeing an increasing scrutiny these days, is around the ergonomic design of a product. For example, if a operator, a customer or an operator, for example, is struggling physically to access any component, then the regulators may view that this will increase the contamination risk, right? The the Sartorius Celsius FFT, FFTP bags, for instance, they are designed in such a way that there is an integrated, if you can see in the slide, there's an integrated line management system for secure tubing, pinch clamps, and also even the end connectors, which are there, like the septic wick or an opta, for example, or any connector that is there. They are easily stowaway, like there's a proper way that they can be stored, and also they have easy access to the lines, right? There are polyester plates that are transparent with the back chamber that's completely visible. So you can see when as the product is frozen or the product is completely thawed during all the process steps, you can see that makes it much easier, no manipulation required. And the container is completely configurable with different kind of connectors, giving you flexibility to the customer to not worry too much about the risk of contamination, because they could have an aseptic connector, for example. So the flexibility with aseptic connections or different types of connectors, and then it is designed in such a way that you can easily wipe it down. So all the surface area is visible and easily wiped down. So when you're entering into like a production area, it is much easy or more convenient for the end user. So, going a little more deeper into this topic, so single-use suppliers, they need to also perform extensive material characterization. So, in order to characterize the mechanical resistance of different materials that are submitted and used, and they have to submit these materials to different temperatures. You can see in the screen here, like 0, -80, -1, -120. So these are, at different low temperatures, so that to identify the most suitable material that can be used for the manufacturing of that single-use component for freezing applications, of course, as well as which portion of that product is not so strong and needs additional protection, right? So this kind of test has to be done by the single-use suppliers. And for this, it's very essential that the customer, not the customer, the manufacturer or the single-use supplier has deep understanding of the polymer behavior at low temperature, and he uses this knowledge for material selection and how the container has to be packaged, how it has to be designed, so that it provides maximum amount of protection in real life scenarios, right? Okay. So now moving ahead, so when we're moving from multi-use like bottles or stainless steel components, for example, to single-use components, and you want to integrate them into your process, okay, then performing extractable validation is inevitable work. Okay, it has to be performed. So the efforts for the single-use ENL or the extractable and leachable validation depends upon various factors such as process step. It depends upon which consumable is being used, what is the product of from the customer, etc. Okay, and the more the supplier can provide the extractable data versus different factors, the easier it is for the end user or the customer. So it is best that when you're selecting supplier, try and see how much of information they have with respect to leachables, with respect to compatibilities, with respect to various other aspects like that. So the extractable assessment or the risk assessment is a key element and the starting point for any ENL validation. So first you need to see whether your process really has, there is a risk involved, and based on that the risk assessment decides whether you want to go further into the leachable studies and things like that, right? So the extractable guide is the tool that provides the first level of data, and that post that you decide leachable has to be done, leachable studies have to be done or not. So this is important, and best to go with suppliers who can support you with data on this. So thus, several levels of data and support can be provided to the end user by the single-use supplier themselves. Okay. Moving on, because let's concentrate more on the latter part of the fill finish, but I just want to also talk about when you handle the freezing components, what other things you could maybe also look into. So one, when there's single-use components, there's always this fear that what if something breaks, so you're concerned because these you would feel like this is a plastic, so there might be robustness must be is something that is always in your mind. So being robust is essential, okay, is essential. But then you also once you have got your product and you want to the product is safe, but then you want to move the products here and there, right? So one, when you're moving your products, say to the DS has arrived to your site, but it is arriving because it might be coming from a different the DS site might be somewhere else and is arriving into the DP site. So the drug substance that you have is coming in a single-use container. It has to be robust, but on the way when it is being shipped, it also needs to remain frozen, right? It's also equally important that the containers in which or the accessories that become a part of your single-use components are also equally robust, and they also are maintaining temperature. So in this case, for example, you can see Sartorius, for example, like Sartorius containers, uh, in combination with their shippers, they have been subjected to ASTM D4169 assurance level 1, okay, for demonstrating a transport robustness, and the ISTA 7D, both summer as well as winter profiles have been done to assess in different configurations and to support the customer, the end user, for example, in defining their shipping routes and their process. So it really helps the customer or the end user when the supplier that they're working with already has worked on these aspects of having a robust system that also maintains the temperature and also has done at least some amount of preliminary qualification and testing themselves. So okay, so I believe I've touched upon some of the key aspects with respect to freeze and thaw in the fill finish process. And now I will hand it over to my colleague Laura to proceed further in the process. Thank you. Thank you for your time.
Thank you, Nidhi. And now the next step is the drug product formulation. So, okay. So the common questions actually for this step from regulators usually is like how was the mixing speed selected and justified, and how do you demonstrate formulation homogeneity, or something like how do you minimize contamination during formulation, any risk assessment supports. So this will be around the mixers you use for your drug product formulation. So based on those questions, actually this may relate to the four challenges during this final formulation steps with your single-use mixers. So first is the inconsistency of the quality of the product and the variability from batch to batch, or leakage, bacterial contamination of the batch. And also, first, do you have any process validation for extractable, leachable, or compatibility test? So based on these four main challenges, first, inconsistent quality of products. So how to ensure your consistency of the product while the mixing? You need to design a better single-use formulation system. The main application here should be homogenize the drugs and excipients for your final formulation. And main challenge will be how to obtain homogenized solution and to prevent your degradation of the products during formulation. So usually we see some key criteria here. First, you need to understand how your product velocity inside your mixing bags, and also should be a sense of the dead zones during mixing. And the last is you should have low shear stress for your mixer in order to impact your product. So how to ensure product homogenize while mixing? You can have a tool such as a computational fluid dynamic simulations. This allows you to visualize your product like vortex formation inside the mixing bag or the fluid velocity profile to show the like side view, front side view or top view. And also this can help you to evaluate the mixing speed, mixing time, and without any dead zone inside the mixers. And also the CFD, this tool can help you to simulate how the powder dissolution inside the bag. So, oh, sorry. Such as this way. And you can see the powder go through over all the mixer bag and it dissolved. And you can see there's still some powder around the corners. And by time passing, the powder just dissolved. So this tool is very powerful, can help you to visualize the fluid and powder dissolution inside the mixing bag. Okay. And also in general, you can also do some experimental data to confirm your product homogenize while mixing, maybe monitor the conductivity or pH, and to determine your mixing speed or mixing time. And usually this is final steps, so your product will be very precious. So usually we cannot really have a lot of big amount of the product to test every conditions. So usually they test on a very small volume. So you need to better select the mixers with well-established scalability model to ensure when you perform the test in a small scale, then it can be easily scale up to larger size, larger scale. Okay. So regarding the shear stress actually is present in almost all bioprocess, and this is the main key factor contribute to protein aggregations and denature. So it may kind of affect the products, and you will get the lower yield of the active products, and also poor performance of the final filtration due to the aggregates or particles. And shear stress is primarily caused by friction between fluid particles due to fluid viscosity, and this mainly around the impeller. Okay, and you can see here there's two types of the mixer impeller, and these are the CFD profile here, and you can see the red and yellow color represent the higher shear stress here. So you can see many shear stress happen around the impeller. So the shape and design of the impeller is very important. You need to understand whether this affect your product, and also the technology of the impeller, whether this impeller is levitating or is the contact impeller. Because if it's the contact impeller, there's also have high shear rate happen on the bottom of the impeller. So those are some main factors you need to consider for your product. So the second challenge, variability from batch to batch. So how to reduce the variability from batch to batch is to better monitor and control all the process parameters, such as like buffer preparation. You need to monitor the pH or conductivity, or for your downstream or final formulations, the temperature. You need to measure the temperature to ensure temperature are there in the certain range. And also you need to monitor maybe pH or conductivity to ensure the homogenize of your mixing. So monitor of all the critical mixing parameters for GMP production with some certain sensors is very important. And how to deliver those data and parameters to your DCS or SCADA system and automatically. This is all important because those the data you need to keep the data integrity and also to increase the efficiency by your process. So in general, the integrated monitoring and control for mixing. First, you see there's a lot of parameters here, sensors from pH or conductivity and the mixing speed and weighing. Those are with different types of the signal, maybe analog or digital signal. And you will need like a I/O unit or the control unit with a PLC. They can just consolidate all the different types of signal into one uniform signal to SCADA or DCS via certain communication protocols. So once your data collected and sent to a SCADA and DCS, so your SCADA and DCS system can better control or execute recipes to control your process. And also most important is to record all the data and reporting to comply with PAR 11 for the data integrity. So for the benefit for this monitoring and control, it can ensure the consistent of quality and also the increase the process efficiency and more reliable and compliant because all automatically tracing and the recording. And also you can check on the SCADA system with real time and to ensure the batch to batch activity is consistent. So for the last two challenges here, leakage, bacteria contamination, and also process validation. So As you can see, the critical attributes in manufacturing process by Annex 1 from upstream to downstream, the more close to the final process, you require more critical attributes you need to consider, like EML, chemical compatibility, integrity of single use, sterility of single use. So most important is the integrity to ensure all the sterility of the single-use system. So the integrity a lot rely on the supplier a lot. Supplier need to provide very robust product to ensure your mixing process is without no issue. So you really need to know the supplier's technology, such as Sartorius. We have a flex-safe film, which with multiple layers with different materials and had been validated and tested over 3,000 tests to characterize the film behavior to ensure the stress flexibility for exceptional robustness. And for the validations for the bag, we also have qualified validation for the package for based on the shipping worst case test. And also we have a lot of testing, mixing, such as at low or high temperature testing for 24 hours. This ensures consistent robustness during the overall product life cycle. And the last is we also have a lot in process control for the bag. Start from raw material, filtration, welding, and assembling. This to ensure lot-to-lot consistency for the bag. So once customer they have got the bag robust bag, then also consider about the integrity. There's also another topics around the leak testing. So there's two strategies customer may can consider is from suppliers side. It can be performed the supplier integrity test in the manufacturing site. This requires specific device, and this detection limit can down to 2 micrometer. So this 2 micrometer is meaningful, is the already validated via several testing to is like threshold for no liquid leak and no microbial contamination. And when the bag delivered to customer site, they can also perform the point of use leak test based on pressure decay test. The detect limit start from 15 micrometer, depends on the size of the bag. So this main purpose at the point of leak test is just to avoid the large amount of liquid leak during operations. So you can have different strategy for your integrity testing for the CCS control. Okay, so the last is the process validation. For sure, the mixing bag is quite close to the final process, so the bag should be validated with the EML analysis and also compatibility analysis. Okay, so that's that's all the overall change for the final formulation part. Now I hand over to Michael.
Thank you, Laura, and good afternoon, everyone. My name is Michael Shafirius, and I'm the Filtration Product Specialist for Asia Pacific, excluding China. Today, I'll be speaking about EU Annex 1 and the implications on sterile filtration. In our flow diagram of a typical process here, you can see a filter integrity tester and a pupset stand. Specifically, what the regulator auditors now expect to see, and also covering some trends in audit findings over the recent past related to sterile filtration and Annex 1. So some common expectations from the regulatory auditors. This is not an exhaustive list. It is really what we see with our contact points in our customer base, i.e. your manufacturing sites and companies. So they really represent some of the key expectations that the auditors are finding and seeing due to the release of EU Annex 1 in a few years ago. So the first I'll cover here is Contamination Control Strategy, or CCS for short. This has been discussed already by some of my colleagues. Here, it is of course also applicable to sterile filtration. Really, the CCS encompasses the entire manufacturing process and must be considered at each step. With regard to sterile filtration and PUPSIT, the system supporting this must be designed in such a way to eliminate risks of contamination at this critical point. PUPSIT and robust risk assessment. So depending on the regulatory agency, there may be a mandate to do PUPSIT or not. However, even with the strictest agencies, risk assessments on the PUPSIT process is expected. If the RA shows more risk to the process than the PUPSIT test removes, there could be justification to not perform PUPSIT. Here, though, you must discuss with the agency in the region you supply to make sure they do support this approach. Next, robust PUPSIT system design. So PUPSIT system designs must be made with the CCS and QRM principles at the forefront. I'll speak more about this in the following slides. In essence, any PUPSIT system should be designed to ease operator interaction and human error control. Automated systems must be consistent and reliable. Filter integrity. Demonstrable sterile filter integrity is, of course, one of the highest priorities of the auditors. This encompasses the filter integrity tests themselves, but also importantly, the filter validation supporting the use of filters specific to the process conditions. And finally, the final point here is quality risk management and how it relates to PUPSIT and filter integrity testing in general. More on this in the coming slides. So pre-use, post-sterilization integrity testing. Let's begin with PUPSIT. Some of you may have heard me speak about PUPSIT over the past years. Here today, I'll briefly discuss what different systems are possible and cover how the regulatory focus may be here. Firstly, the overall design should be considered. Will it be stainless steel or single use? Here, each material will have different design requirements. For example, stainless steel will not have pressure limitations for this process, but will have additional on-site considerations around assembly, sterilization, and handling. Single-use systems, on the other hand, may have pressure limitations, and the integrity test method should be considered carefully around these limitations. For example, bubble point testing may not be possible in some cases with single-use systems because of pressure limitations. You can imagine a 0.1 micron filter has a very high bubble point, and this may be well beyond the pressure limitations of a system, and therefore diffusion testing could be used in this case. Next, is the PUPSIT performed with a wetting agent of product or water? So what should be used here? Product, buffer, water? In my opinion, product should not be used, as it negates the reason behind PUPSIT that is being performed in the first place. So using buffer or water to wet the filter then adds the necessity to have a sterile drain or collection method for these wetting agents. Here lays one of the risks mentioned earlier on PUPSIT designs, and critically must be considered in the CCS and also QRM ideology. Design aspects around your PUPSIT systems must take into account the wetting method that you're using. It is possible to perform PUPSIT in a single-use set held freely on a benchtop. These designs have inherent risks associated, as the filter may not be wetted efficiently, or worst case, vent or barrier filters may become blocked with fluids, preventing successful filter testing. With this in mind, to increase the quality risk management of a manual system, racks or shadow boards are key requirement here. So this is really a supported manual system. And you can see the picture on the right represents a supported manual system of this description. These also offer a way to reduce manual system handling errors and also critically hold the filters in correct positions to minimize false test fail or pass results. However, the penultimate system to consider here will be an automated system, which will basically cover off all of the required best practices, if you like, and the highest risk mitigation for this process. So earlier I mentioned quality risk management and how this is a critical part of Annex 1 and what the regulators are expecting to see. So how does this look? I have here an excerpt from Annex 1, and you can see here that highlighted some text, but critically QRM applies to the entire document and will normally be referred to in specific, normally not referred to in specific paragraphs. So the focus here from Annex 1 and the expectation from a regulator or auditor is to have quality risk management built into your entire process. So what does this look like? Is it quality by design instead of quality by testing? Certainly. And the text highlighted here drives home that point, particularly the last highlighted text here. Monitoring or testing alone does not give assurance of sterility. So you must be thinking about your process as you design your process and the systems that you put in to support the process. Critically here, though, we're talking about filter testing and PUPSIT systems. So the nightmare of all quality assurance should be a false pass result. So in context of filter integrity testing, you have performed your integrity test, the batch is then released, and you find out later that that particular test was actually a false positive. Obviously, false failed results can also happen, and this is really a deviation in your batch report. You might be releasing the product later than you expect, and it could cause a drug shortage, but at least there's no hazard or risk to the final patients. So in regards to QRM, in this focus of integrity testing, we can break this down into a couple different points. The first being operator errors at the point of use. So critically here, we're looking at training of operators and SOPs that are made mandatory to reduce the likelihood of human errors. These must be well scripted, thought out, and the full process aligned with what the actual SOP says to reduce those problems. Next, education keeps operators alert and further reduces the likelihood of human errors, but there is always still risk. So then we can introduce the idea of program-specific parameters in a filter integrity tester to limit and allow early detection of human errors. And how should that look? Inspection of test results and electronic signatures by the operator and QA confirm the validity of the test result. I know from personal experience, often when I'm doing training on integrity testing and integrity testers in general, we often don't have staff from QA functions present. But this is critical. QA need to know how to read a integrity test result and what a failed test looks like, what a pass test looks like, so that they can detect at that point what those errors may be. So critically, in integrity testers, you can build in some of this functionality already. Here, we've highlighted a screenshot from our own integrity tester showing filling time maximum and filling time minimum, which can give already indication to the unit whether the correct filter is being tested. So the next point to consider is operator errors at the point of use. So as the test is being applied to the filter by the integrity tester. So even with training and perfectly written SOPs, human errors will never be avoided to 100%. Upstream volume can be a measurement used by the integrity tester to detect if there is a test setup. So in the picture I'm showing right now, we can, by programming in an expected volume that the integrity tester might measure, determine whether the right size filter is being tested for that specific program. Or it could detect whether a filter is actually being connected in the wrong way, and you're testing the filter backwards, which would be a catastrophic test failure and, heaven forbid, a test pass. Or a closed vent valve between the filter and the integrity tester. This is fairly common. I've seen it many times, or this could also be a test line that is not being connected to the filter correctly, or a broken filter with a downstream valve that's closed. So after the filter, the valve has been closed for some reason, and effectively you end up pressure testing the line rather than testing the filter. And again, that false positive test may allow you to release the batch to market. So how does that look on our specific unit? We have a minimum volume and a maximum volume setting that can be set for any particular test program to help detect these specific test failure results or abnormalities. But additional features may also be designed into filter integrity testers to increase QRM and should be considered. For example, the cleanability of the tester internal components. Is that possible with a particular tester? Programs to block repeat tests. So for example, after 3 tests on the same filter, can you block those programs and then require a higher level of sign-on to unblock and escalate that as required? And finally, data integrity design security features may be designed into integrity testers. There are many more features, and this isn't designed to be any comprehensive look at integrity testers themselves, but look into those kinds of ideas when you are considering your processes around filter integrity testing. So moving on now to some recent regulatory findings. So these are probably the more common things that we're hearing about that you can view online on the FDA's websites, on the EU, and etc. Specifically, we're focused here on sterile filtration and how the auditors are applying EU Annex 1. So the first point here, the validation must be performed with all critical process parameters considered. These should include maximum differential pressure on the filter, maximum product exposure, minimum and maximum product temperature, and any indigenous organisms that or process isolates that may be present in the product. No PUPSIT or RA risk assessment on PUPSIT. So critically, with so much regulatory and industry focus on PUPSIT, there must be either PUPSIT in the process or an RA from the manufacturer, the product manufacturer, that is. Operator confidence in PUPSIT operation. So PUPSIT systems can be quite complex, which is why the system lends itself to automation in order to maximize the reduction in quality risk. As many different operations must take place on the same fluid lines to correctly perform PUPSIT, operators must be highly trained in the correct procedures, and systems must be designed with functionality in mind. This is most critical with manual setups. The next point is related to the first example given here. Filter validation studies must reflect the actual process. Here, consultation with professional filter validation specialists is strongly advised. Design of PUPSIT systems is critical. There must be process flows that maintain the CCS and prevent operators from any intervention of the sterile pathway. With poor designs, operators may be forced into interventions. In PUPSIT systems, designs must have gas flows both into the system for integrity testing and exiting the system for venting of the filter during wetting or allowing free passage of air downstream of the filter during the integrity test. Here, sterile vent filters should be present and managed accordingly to prevent blockage of the vent filter and maintain sterility. Vent filter integrity control. This is a similar discussion space to the last point. Vent filters must be integrity tested before use. With system designs for PUPSIT, the reliable integrity testing of the vent filter must be considered. Some designs incorporate 2 vent filters in series for this reason. If product accidentally contacts the vent filter, what is the impact to the post-use integrity test? Will you get a false pass on the vent filter? The final trend in audit findings here is around poor test failure handling. There should be an SOP and training in place to outline how filter test failures are handled. It is generally accepted that only 3 tests should be performed on a sterilizing grade filter before escalating to or involving the filter manufacturer. Each test would look at different aspects of test failure. For example, leaks, insufficient wetting, and improper test program. A good summary of this approach can be found in PDA Technical Review 26. So in conclusion, regulators are expecting POPSIT systems and sterile filtration in general to be well considered alongside each site's CCS and also designed and managed with QRM principles at the forefront. I'll now hand over to my colleague Dixon to talk about the end parts of the process.
Thank you, Michael. So, hi everyone, I'm Dixon. I'm the product specialist for final filling for APAC, excluding China. For my segment, I'll actually be covering the last two segments of the fill and finish process, namely the aseptic transfer and final filling. We will actually explore what are the core considerations at each of these steps and our experience with customers and regulators on these two areas actually pertaining to Annex 1. While these two steps seem simple on this infograph, the truth is that this is one of the most complex and critical process. What you see here is a typical line for aseptic process and final filling, and you can see that it actually involves multiple steps and machinery. One thing that you will immediately notice then is that there is a rapid use of isolation technology at these steps. This is actually consistent with the latest regulatory guidance, such as Annex 1, where there's a push towards isolation technology around the filling area. In fact, it specifically mentioned that wraps and isolators are beneficial to reduce contamination, and any alternative should be justified. This means that wraps and isolators are basically mandatory, and they should be used unless you have a proper justification. But why is there such a strong push towards barrier technologies? The answer is simple. This is because of human risk. As you can see in the picture, a typical process requires manual intervention no matter how controlled or automated a process is. One of the most important realities in sterile manufacturing is that people are both necessary and dangerous to the process. Annex 1 actually strongly emphasizes intervention reduction because regulators recognize that every manual intervention is a chance for contamination. But why is that? Why is so harmful about manual intervention? So actually humans generate particles and can bring contamination into your process. Operators can also make mistakes during the process, thereby breaching sterility or generating contamination risks. Manual intervention depends heavily on operator aseptic processes and behaviors, which is hard to enforce and train. And operators can also disrupt their existing protection mechanisms through their apparent behavioral patterns. So regulators are not unreasonable. So even though inspectors also recognize that human interventions are necessary, but they also know that they are unavoidable. What they want to see then is an effort in reducing the intervention, a controlled intervention protocol that considers the appropriate risk, and also a system that categorizes, qualifies, and justifies these risks clearly. They will often review how many interventions per batch, whether these interventions are avoidable, whether you could have implemented automation to reduce them, and whether these are actually scientifically evaluated. What they are looking for really is a focus on intervention maturity of your site. There's also increasing scrutiny around ergonomic design or process ergonomics. This means that they want to check whether your process actually complicates or confuses the operators. They want to see whether operators struggle physically to access components, and whether the process itself introduces any awkward movement that leads to airflow disruption or accidental contact. Regulators do not simply stop at CCS's documentation of human intervention. They also now spend substantial time observing operators directly, because actual behaviors often differ from SOP's expectations. Common observations include touching non-sterile surfaces, excessive movement, operators leaning to first air, poor transfer techniques, inconsistent glove sanitization, for example. Inspectors are no longer satisfied with simple training records. They increasingly ask, how do you know the operators truly understand aseptic behaviors? Some strategies different sites use can include operator different sites use can include operator observation programs, behavioral trending, intervention scoring, and aseptic coaching systems. All these in order to reassure regulators that their operators are trained and compliant with aseptic behaviors. Since we have really established that human risk is a universal concern in aseptic drug manufacturing, we will now look at concerns that are more unique to aseptic transfer. When we talk about aseptic transfer, we must also consider the expectations of regulators towards barrier technology used like wraps or isolators. So what's the point of the isolators? The key point for the use of these isolators and wraps is to serve as a contamination barrier. So as such, regulators place higher emphasis on the aseptic integrity of the barrier system. They will frequently review aspects such as leak integrity, PHP cycle, glove testing, transfer system, and very importantly, recovery after interventions. The main rationale is then that your barrier system must be able to isolate critical zone activities from the human risk and thereby reducing the chance of contamination and maintaining a sterile boundary. So in this use of isolation technology, particle control and first air protections are key criteria for regulators. From an EU GMP Annex 1 perspective, regulators do not simply look at whether particle counts pass specification, but they expect you to understand, minimize, monitor, trend, and investigate particle generation, particularly in grade A critical zones and wraps in isolator spaces. The emphasis is on preventing particles from ever reaching the sterile product because particles can carry microorganisms and compromise your first air protection. Regulators will want to check if you have all your potential sources of particles identified and efforts made to reduce them. They want you to have assessed all personnel movement and behavior, PPE materials, gowning, and sanitization practices. They want to see whether you have a system in place to monitor particle count within the isolator and have a means to trend them so they can identify if your system is within control and react to any risk before it becomes an excursion. They want to see all these measures clearly documented into your CCS, and they want to see the complement of particle control with your first air and grade A conditions. First air is another important and aggressively inspected topic under Annex 1. First air is actually the uninterrupted unidirectional filtered airflow. And Annex 1 often offer insights into how operators can ensure first air is most effective and uninterrupted over critical zones. They pay close attention to anything that disrupts grade A airflow to the sterile product contact surfaces. So they want to see data to demonstrate uninterrupted airflow. They want to see whether your stopper bowls or critical areas will have any shadowing. You want to see whether there's any poorly positioned filling needles or glove devices. This is important in fill and finish because sterile products is highly exposed during this filling process. And they expect facilities to understand airflow behavior in detail and not just conceptually. Regulators will usually ask, how do you know first air protection is maintained during this intervention? And if you only rely on assumption rather than demonstrated evidence or studies, then your facility becomes vulnerable towards the regulatory scrutiny. Regulators will want to see if you have studied the time required for airflow to recover after intervention. And at critical zone areas, they also expect to see validated studies about airflow behavior and turbulence in order to analyze the risk of particles and contaminations being brought into the critical zone via air turbulence. Aseptic transfer is important because this is the step that ensures that the product is able to enter the critical zone area while maintaining the contamination barrier of your process. For aseptic transfer, regulators will observe whether sterile boundaries are actually maintained and whether there's error during the pot usage. They will expect a robust and comprehensive CCS where you have performed validation studies demonstrating sterile transfer under worst-case conditions, their repeatability, and procedures for managing failed transfers. So at this area, for aseptic transfer, choosing the right product from the start can make it so much easier to justify to regulators about your aseptic transfer process. Certain products can make it inherently easier to tackle certain regulatory concerns. For example, Sartorius' BioSafe pods use magnetic docking. This magnetic docking drastically minimizes the particles generated and reduces operator error rate. This will immediately help to reassure regulators about these two risks. Our pods also only have one mechanism outside of the isolator, which means that any particles generated from the pod are outside of the isolator and not inside, which is the lesser of two evils. Our magnetic doors also latch on automatically and removes operator uncertainty in door operation. And we have the smallest ring of concern in the market at 0.1 mm and 0.01 mm respectively, which helps to maintain the sterile boundary. Our pods can be operated entirely from the outside, meaning that there is less particles generated within the isolator, and as well as less risk to the disruption of first air protection. In addition, our BioSafe 200 has been designed to be Annex 1 friendly from the ground up, and has even more features to help eliminate operator error, so thereby allowing our users to more easily reassure regulators about human errors. Last but not least, I'll be covering final filling, especially single-use final filling. So final filling is one of the main areas that evolve together with Annex 1, and it's something that the industries are keeping a close look at how to best prepare for the future. The main application at this stage is basically the aseptic transfer as well as drug repartitioning. So this is at the stage where Annex 1 becomes a lot more prescriptive. For example, like I mentioned just now, they have mandated the use of isolated wraps and aseptic transfer pods. Regulators will actually want the product to transfer to grade in an aseptic manner, and they want that the filling volumes are controlled and within specification. The key challenge for this portion is then not to only maintain your sterile boundary, also to prove your filling accuracy and reduce your human intervention. So again, making the right product choice right from the start will go a long way in reassuring regulators. Other than dosing pump calibrations, filling accuracy can also be affected by your consumables. So our Octopus bags are wallet shaped, which allows fluid to pool evenly and stabilizes the flow rate. A bonus is that this shape helps with product recovery as well. Our dosing lines are also spaced to ensure that each line has an equal cubic volume of product, which is important in ensuring that the lines don't have to compete with each other for a drug product, even in high-speed filling scenarios, thereby stabilizing your flow rate and filling accuracy. We also have vent filters in our bags to prevent the bag from inflating or collapsing during continuous filling, which then stabilizes your flow rate. And lastly, our flex cell film has been in the market for 20 years, and we have a robust E&L data for it. All these will actually help to reassure regulators about the filling accuracy of your line. Single use is also an increasing popular topic in the Annex 1. So, as I'm sure what some of my colleagues have already mentioned, so single-use technology adoption continues to accelerate in the aseptic fill and finish because of its flexibility and contamination reduction advantages. We can see it tick a lot of checkboxes in Annex 1. So they are made on purpose, application tailored to your process, and hence do not add an additional layer of complexity to your process. They can be provided as closed system and so are sterile, and they do not require any CIP and SIP, which will have to be validated, periodically requalified, and always monitored in routine processes. They also come pre-assembled, right? And so you don't have to run the risk of operator misassembly. And they are also pre-validated, making it possible to perform product and process-related validation activities in a very fast time. Additional benefits you must understand is that remember that regulators also expect QRM and CCS to be applied on all steps of the process chain. In a traditional stainless steel system, that means that all the responsibilities are managed by you. But if you use your if you choose a good single-use provider, you can actually share those responsibility with your single-use providers. You can actually transfer a good portion of your responsibilities like sterility validation, proof of sterility, supply chain reliability, multi-sourcing, etc., to your single-use solutions provider. However, that doesn't mean that once you use single-use, regulators will not have any concern. They actually expect you to demonstrate strong technical understanding of these systems. They expect you to know your E&L interaction of the film materials with your products. They expect you to have done a sort of design complexity analysis to see whether it adds an additional layer of complexity and runs the risk of increasing operational complexity. You also want to see attention to structural integrity testing, sterility validation, and aseptic processing. So all these are things that you need to know. But if you work with the correct single-use solutions provider, you are actually able to obtain support for all these concerns or regulatory considerations through the single-use solutions provider. So choosing the right vendor will allow you to reap the benefits of the single-use system, but also have the support in answering regulatory requirements. So in conclusion, fill and finish is a complex process that extends from freeze and thaw all the way to final filling. With the new revision of Annex 1, the demands of scrutiny of your fill and finish process has never been higher. However, the answer to Annex 1 compliance might be more simple than we imagine. Regulators don't expect the most successful facilities under Annex 1 to be the most complex or expensive facilities. But in fact, they're actually the facilities that deeply understand contamination risk and manage it systematically. And that's all for my presentation. So I'll hand it now back to Imapek.
Thank you very much, Nivedita, Laura, Michael, and Dixon, for the very insightful presentation. I hope the audience have learned a lot from the valuable sharing session. And now we will proceed to the Q&A session. Once again, attendees, if you do have any questions regarding the presentation, please feel free to submit your questions by using the Q&A function at the bottom of your screen. And since I can already see some questions coming in from our attendees, I think we can start with the first question. Okay, so the first one would be, okay, how do you ensure sampling does not compromise sterility? So who would like to take this question? Is it
I
Laura?
think I
Ah,
can
yeah,
take this question.
sure.
Okay. So, yeah, sampling actually you should perform through kind of like sterile sampling devices, such as a cleft connector, which is a valve inside to allow your fluid can go outside only, cannot go inside. And also, this device should be validated how many times can be sampled to remain aseptic. And also the sampling frequency should be minimized based on your process requirements. And all the sampling activities should be conducted using validated aseptic techniques. Okay.
All right.
Yeah.
Thank you very much, Laura. I think we can go to the next question. It's coming as anonymous, but they are asking, how do we ensure that during aseptic transfer, the first air protection is not disrupted? I think aseptic transfer, maybe Dixon, would you like to take this question?
Yeah, thanks, Lou. So yeah, sorry. So just because me and Laura are in the same room, so there's some feedback. Okay, so regarding first air disruption, this is a topic that's very popular with regulators, right? But the trick is that they actually don't expect a complete sort of like prevention of first air disruption. Rather, what they're looking at is actually how whether you have actually done your airflow study, airflow visualization test to actually see how fast it recovers. So the trick to this question, or answer to this question, is then about your first air protection recovery rather than a prevention of the disruption.
All right. Thank you, Dixon. Now we move on to the next question. All right, this is about POPSIT, so maybe it's about for Michael. Should POPSIT occur inside the Class A area? What do you think, Michael?
So this is actually a question that has come up a number of times from our customers, both in Asia Pacific, but also across the world, really, North America and Europe included. I think the answer to this is if you do read Annex 1, and in great detail, as many of us have, there is a section in there requiring the filter to be as close as possible to the filling needle. Now, that might describe a situation where POPSIT would be inside the Class A area. However, this must be also read in terms of quality risk analysis and management for the entire system. So the practicality of putting POPSIT inside a Class A would actually negate some of the handling that you need to do within Class A to maintain that environment. So the number of manipulations you need to do on a POPSIT system really pushes it outside the Class A area. And then keep in mind with a single-use system or even in a stainless steel that your control around the POPSIT system itself maintains the critical sterile barrier, if you like, for the product. So the design of the POPSIT system with vent filters, maybe dual vent filters, and these sorts of considerations maintain sterility. On top of that, we haven't heard yet from any auditors or audits where this has been cited that POPSIT is sitting outside of Class A. Thank you.
All right. Thank you, Michael. Now, there's another one about POPSIT. They're asking, are critical van filters also required to have a POPSIT test?
Always many questions about POPSIT. It's the hot topic of the last 5 years, I think.
Yeah.
So the simple answer here is no. There's no requirement at the moment. It has been discussed, I guess, a lot on conferences and these sorts of things, but no auditor has requested this in the past and not in the foreseeable future. I would also say that if you read the regulatory documents, Annex 1 included, vent filters specifically are considered in a slightly different way to liquid filters. So the answers for this can be found within Annex 1. Thank you.
All right. Thank you, Michael. Now, they're asking, what happens if mixing stops unexpectedly? I think this is related to.
Okay, I think I can take
Yeah.
this question. So for this mixing start unexpectedly, kind of like mixing interruption, this should be managed according to predefined procedures. It should be one of your mixing study for this. So you need to see whether this may impact your product by evaluate some like your formulation characters or homogeneity studies and during your validate holding time. So you need to evaluate based on your interruption durations. So once everything impact, you just evaluate, then you can decide whether this mixing can start or not. So this based on your mixing study and interruption. Yeah.
All right. Thank you, Laura. I think we can take one more question. This one last question is asking about what are the common observations raised for critical zone areas?
Okay, maybe I can take this. So critical zone area is actually where your more or less your filling occurs, right? And what usually other than filling accuracy and maintaining sterile the sterility barrier, as what I mentioned in my presentation just now. Another big thing that people will actually or regulators will actually look at is about different air protection. So the critical zone areas will have their own air protection. And commonly during when you're doing your final filling, right, your conveyor belts will be bringing your valves over to the filling area, the machines will be moving. So there will be a lot of turbulence. what regulators actually want to look for is whether you have done your airflow visualization studies, right? To see whether you have studied the airflow turbulence sort of pattern, whether it goes up to your filling area, right? Because if it doesn't go up to the filling area, it means that any particles that might have gone through your first hand protection will be safe, will not go into your valves or needles. Whereas if you see that the airflow turbulence reaches your valves or your exposed needles, right, it means that there's also then a chance that any particles that have managed to sneak through your first hand protection using the turbulence will also likewise be able to go into your filling needles or valves. So they want to see whether you actually have done your airflow visualization studies in this area, especially airflow turbulence, right, for critical zone activities.
All right, thank you, Dixon. Is there anyone else who would like to add to that answering that question? No? Okay, all right. All right. Thank you very much, and Laura, Dixon, Michael, and also Nivedita for clarifying the doubts of our attendees for today. As much as we would like to address all questions from the attendees, in the interest of time, we will have to wrap up today's session. But not to worry, any unanswered questions will be submitted to our speakers, which will be answered offline and shared with all attendees via email. I hope you all enjoyed being a part of this webinar and found the presentation and discussions to be very insightful. IMAPAC would like to extend our heartfelt gratitude to Sartorius for making this webinar possible, and a big thank you to the audience for being a part of this and making this webinar a success. On behalf of Sartorius, thank you and looking forward to welcome you again at the next webinar. Bye-bye.
Bye all, and thank you.
Bye.